Okay, so hello everyone. Welcome to this webinar, Bringing Development of BrainChip Akida Neuromorphic Models to All. I'm going to pass you over shortly to my colleague David, who is from Edge Impulse, and will kick off the webinar. During the session, if you'd like to ask any questions, please pop that in the Q&A box. You can also upvote in there, so if you would like to upvote any questions, then we can get to those at the end. We've left plenty of time for Q&A, so yeah, please do add your questions in there. Okay, and with that, over to you, David.
Hey everyone, glad you could join us today. I'm excited to be here with Todd and Nikunj from BrainChip to give an overview of Edge Impulse, the BrainChip Akida platform, and how we've been working together to enable rapid prototyping of machine learning algorithms for neuromorphic compute. So to get started, I'd like to give a quick overview of both Edge Impulse and then pass it over to BrainChip to discuss their platform and technology, as well as show some demos. And then we'll go through the process within our kind of current integration with the Akida platform of building a model in Edge Impulse, deploying it out to hardware, and seeing how it works in the field. We'll then discuss some future work and some kind of cool upcoming things that you can check out in the coming months. And then we'll do a short Q&A. So to start, I'll give kind of a brief overview of the Edge Impulse platform. For anyone who's not familiar, we're a fully integrated ML platform focused on edge machine learning and embedded deployments. We provide developers with a holistic platform for ingesting data, experimenting and exploring different algorithms to process that data, and then deploying it out to their hardware in order to run those models in the field, have confidence that their accuracies and performance match what they need to solve real problems, and doing so in a completely open source, non-black boxed way to give you the confidence and freedom to kind of customize things as needed for your specific problems and use cases, and understand kind of what's going on under the hood. So within the platform, we provide a host of tools around building and ingesting data sets. You can collect live data from the actual sensors that you are running in a test system or in a field rig, as well as pull in large data sets from external sources, from image data sets, sensor fusion, audio data. The platform supports all of those in a unified interface, and it allows you to manage those data sets in a scalable way with our kind of cloud infrastructure backing everything. On the algorithm design side, we provide both pre-existing blocks and functions, both for feature extraction and signal pre-processing, as well as a variety of different learning algorithms. And this is kind of where later in the webinar, we'll kind of talk about how this all plays together with the BrainChip Akida platform, as well as kind of what options are available today and what we'll have ready in the future. Along with this, we have kind of AutoML and collaboration tools that will allow people to rapidly kind of explore the space of different algorithms and approaches and compare their performance, as well as sharing those kind of results and easily working across distributed teams. So with that kind of brief introduction out of the way, I'd like to hand it over for the really interesting stuff to Todd, who's going to kind of go through an overview of the BrainChip Akida hardware, why it's so cool, and everything about that. So take it away, Todd.
Thank you, David. My name is Todd Vieira, the Director of Customer Engagements at BrainChip, and I'm here with Nikunj Kotecha, who's one of our machine learning solutions architects. And with that, let me tell you a little bit about BrainChip. So BrainChip has over 15 years of AI research. We're the worldwide leader in AI on-chip processing for neuromorphic computation. And we have been featured in several articles. And one of our most recent articles, I'll show you a little bit about that, is the Mercedes that was launched at CES this year, the EQXX. The next slide. So talk about Akida and our runtime engine and how our edge-based processor works. It's meant to take in any sensor, whether it's vision, audio, olfactory, tactile, and various other types like LiDAR, radar, or ultrasound. We do some pre-processing beforehand, and then you come into the Akida IP. Now, this is meant to be an edge-based device. So we take those edge device models, and we can run those as standalone on our hardware to highly optimized system that is optimized for power, efficiency, and overall systems optimizations. And then we also can work in conjunction with the CPU of the host to handle bigger, larger models, and depending on that complexity, in conjunction with the host CPU. So first, I'm going to show you a demo of 3 different demonstrations I'm showing. The one on the left is a facial recognition in cabin. The one in the center will be keyword spotting with also voice identification and visual wake. So as we start this demo, you will see it in action.
Hey, Akida.
Aaron, all systems active.
Hey, Akida.
Todd, all systems active.
So as you can see here, we have facial recognition in microwatts to milliwatts. We also ran the keyword spotting to notice the Hey Akida keyword. And we also have visual wake word. So all 3 of these networks can be ran simultaneously to have an enhanced cabin feel. And as I said before, next slide. So Mercedes-Benz announced earlier this year at CES, they used us for their keyword spotting in their concept car that was really focused on BrainChip's neuromorphic computation that they say was 5 to 10 times better performance and power than traditional AI solutions. This is currently touring Europe, and if you get a chance, you could look at various articles that are on the web. Just search for Mercedes and BrainChip, and that'll be, out there. With that, I'm going to hand over some technical presentation slides to Nikunj. Nikunj, go ahead, take it away.
Thanks, Todd, and it's very nice to be here, everybody. So let me talk a little bit about our BrainChip Akida IP and what's a differentiating factor about it. We've built this neuromorphic chip, which is available today for anybody to test out and validate our neuromorphic design principles. You can run your own custom models, or you can use one of our existing ones and leverage the neuromorphic, low latency and low power for AI inferencing. So one of the key things that we do is at the inference level, we do low bit precision computation for both weights and activations of your neural networks, and it can range anywhere from 1 bit to 4 bits of it. One of the unique thing is we can run your custom, your current conventional ML algorithms. We've designed event-based versions of it, which you can convert that to SNN versions and leverage those existing algorithms such as simple CNN or feed-forward CNN, convert it to SNN networks and leverage the neuromorphic design principle and infer that in a low power and low compute environment. One of the unique thing is, we have at memory compute. So each of our engines have dedicated memory, and we do distributed computations for individual layers in the network. So this allows for parallel computation, lower data movements as well. The other unique thing is we take advantage of the low leakage memory on our chip, and essentially we are able to run AI inferencing, giving real-time FPS at much lower clock speeds and independent from your other system or your host system. So this really allows customers to build a very efficient design where each component is responsible for its activity, and the AI component will be offloaded onto Akida, giving you the best performance possible. And another unique thing we have, which is called on-chip learning, and this allows customers to be able to have learning capabilities on the device itself. And our customers are, thinking very unique ways on making these devices personalized enough with this on-chip learning algorithm, where it can range from many different applications where it's authenticating a user to access a particular device, or if it's in an audio domain, it's identify keyword spotting, maybe having a custom keyword that only the user can share and can build out of it, or having family members inside an automotive vehicle. Individual members will have respective settings for in-cabin, for their heat settings or for their entertainment settings. So it's widely used today, and our customers are building their own custom models that leverages this on-chip learning algorithm. So I like this slide very much because this kind of explains, gives a very high-level view of how our convolution operations, once we go to spike domain, differentiates from a traditional convolution. So if you see the top box, this is how traditional frame-based convolution is done. You have a 5x5 activation map, and you have a 3x3 kernel map. And for a convolution layer, the kernel is placed on a central location on the activation map, going row by row, column by column, in order to obtain a particular result. Now, in this, we're doing all computations that are possible. So in this example, we're doing about 225 max of compute. When we shift to an Akida event-based domain, so when this layer gets converted to our hardware, what we kind of implement is just look at the event values and within the activation maps, and only process these kernels on these event values. We still get the same result, but the difference here is we don't process any non-event values or the zero values, because anything that you multiply by zero, you still get the answer as zero. So it doesn't really hold real value to it. And so with this, we are able to neglect many of the computations within the entire architecture. Now, customers see this as a huge benefit because, in networks, you have these activation layer like value, or you have these layers like batch normalization. And if you're familiar with the operations of these, they center a lot of these values around zero, right? So every layer might have a different, sparsity within the activation map. And this changes dynamically with respective different inputs, right? So on an average scenario, Akida, when you convert your algorithms to an Akida domain, we do 50% less number of compute, which allows you to do be very low latency for any neural networks that you run on Akida. And thereby also it consumes much lower power by doing a lot less compute than any other DLA or any other accelerator that is focused more on accelerating or these operations very efficiently, right? So this is very beneficial. And the other thing is we also do 1 to 4 bits. So your network becomes a lot more sparser when you compress your bits down further and further from your training. And essentially, this kind of indicates that we're taking best of both worlds, where we do this traditional training in maybe CNNs or a TensorFlow environment. You get the same accuracy when you convert that to event-based. but now you get benefits of running the SNN version of it, getting much lower power and much lower latency on running it on the Akida hardware. Back to you, Todd, on this particular demo. He'll explain to you on what we did with this demo, and we're working with an event-based camera on it.
So one of the nice things about Akida, I think I had it on our second slide, any sensor. And what we're doing here is we're taking a gesture recognition demonstration from an IBM data set. And what we're doing is we'll be processing those events directly from an event-based prophecy camera at a very low latency and very low dynamic power. So go ahead and run this demonstration, and you'll be able to see as the person in here is doing a right-hand wave, it's registering that, classifying left-hand wave, and we go through clapping, and we go through air drums and air arm roll. And you can see how the accuracy is very high, but the latency is only 2.4 milliseconds. And the nice thing about this is we're bypassing a lot of the data that you don't really need, and only bringing in the samples from the event-based, with the dynamic power being less than a milliwatt. It is one of the nice ways that you see some of the technology being adapted in our AI engine. Now, there are similar types of technologies, whether it's LiDAR, ultrasound, or radar, that you'll get similar sparsity that takes advantage of these the data that's coming in to have a highly optimized system. So with our scalable and flexible IP, it's really important to know that the chips that you're designing, we have a lot of different dials to fine tune your system for the solution that works best for you. A lot of people really focus on performance and tops. It's like, I need a 4-top, 8-top, 20-top machine, okay? But when it comes down to it, a lot of people are also driven in the marketing side by the silicon area. And with one of our unique features that we have in our Akida Edge processor, I can scale up my scale down the area that I'm using and use it in what we call multi-pass mode to allow you to have a smaller node that'll do the same amount of computation needed for a much larger area. And then we also have different areas to play with on the memory. So we have at compute memory, as Nikunj said, and we have the capabilities of going from 50, 75 to 100 kilobytes of memory at each one of our NPU processors, and really optimize the system for your compute needs. And then we also quantize with MetaTF. And here we go. Here's another demo. I'm going to hand it back to Nikunj, talk about this NVISO demo.
Right. Thanks, Todd. So we partnered with NVISO on enabling, taking Akida to a real life application. And they have a nice SDK which does in-cabin monitoring. And as you see on the picture on the left, they were able to run all the models within their SDK onto our reference chip, which we call it AKD 1000. And it's available on an PCI board. Currently, it's hooked up to the NVIDIA Jetson Xavier, which acts as a host system for your application. So let us see how the SDK functions and how we are able to run these multiple models on Akida.
Labeled as driver, co-driver, passengers, and so on. Then each driver independently, it's analyzed for facial landmarks and head pose, which are needed for the whole system. Also emotions, age, gender, and face identification.
Okay, and that's coming from a camera inside the car?
Yes, the camera is up here.
Okay.
Connected to the board, powered by the car system, and also a screen for.
So as you can see, the nice part about this is, this is being applied in a real life environment, and we are running all in a low bit precision models. These models, they have body pose detection, they have face detection, they have palm detection. They also have occupancy registration, and then emotion out of this. So all of these models, they were able to port to Akida platform within a week. So if you really have this stuff built out currently existing, it's really simple and easy to be able to port it with our tool set and be able to run it on our reference board to see for yourself how the advantages that you can get out of this neuromorphic technology. In this case, they were burning so much of power with the NVIDIA box, but they were able to bring it down to a couple of milliwatts just for all of these models by running it on Akida. So we went ahead and did some, performance analysis for these particular models. And as you can see, the latency for, the best performing on each of these hardwares, we outperform those models by a lot. And essentially, if you notice, we're running on a lot lower clock frequency compared to GPU. So if we scale it down, if we scale up to have equal performance, let's say 1 gigahertz for all of the devices, we outperform the GPU and also the CPU by a very large margin. The other thing is, which is I would like to highlight is, the 4-bit models, you still get the same accuracy, but there are other advantages to it as well. If you see the size of all of the models that run on Akida, that's at par to one of the average models that we are running it on the NVIDIA box. Now, this is very essential for customers who are looking at IP or trying to build their own SoC or their modules, because system bus bandwidth is something that is of grave importance for them in order to achieve the performance numbers that they're targeting for. Now, if you're running very low bit precision weights, and they are like 4 bits weights, there is a not much load on the bus bandwidth in order to feed the hardware for the FPS or the latency that you're looking for. The other advantage is, because we have at-memory compute, this also pushes a lot more further, where you store these models on the IP, and essentially you offload a lot on the bus bandwidth, and you're just running a very small amount of compute, enabling you a lot more offloading for the bus bandwidth, giving you a low latency and ability to achieve the latency targets that you are aiming for with your accelerators. So, it is very easy to build models, to use our existing stuff today. And I'm very happy to share that we have this existing software framework called MetaTF. And you can visit our URL on the bottom right over here. It's called doc.brainchiving.com. And essentially, you can land up on this page and download our packages that will enable you to use some of our existing models that we have as a part of our model zoo. And also you can build your own custom models, whether it can be a TensorFlow environment, CNN based, or you can, if you're familiar with SNNs, you can build your native SNNs as well. So this really allows you a nice framework to understand how the Akida IP works, to test it out, to run it on a simulator, or to run it with the hardware that we provide. We also provide some examples for you guys to begin with your own custom models. So it's a very nice starting step in order to use one of, let's say, transfer learning or converting these models to an SNN framework. Back to you, Todd.
Thank you. And one of the questions we had, are our development kits available? Actually, we have several development kits available. There's a Intel x86, which is the box on the left, and a Raspberry Pi ARM-based system on the right. And we have PCI Express cards that could go in any Linux system. If you go to shop.brainchipinc.com, you can purchase those. You can contact myself at tvr@brainchip.com or sales@brainchip.com. And you can get access to these development kits for both development, benchmarking, and just maybe you're just interested in playing around with them. And then finally, I want to show you our latest demo, Any Sensors. This one we kind of integrated with real life experiences with our, the smart infrastructure that's going around. Go ahead and press play. We have a train running. We're going to do smart infrastructure. And we actually have a small train set. And if you look here, it's going to show the vibration sensors. And right below that, there's these little motors. And what we can do as we analyze the vibration that's from these motors, we can show normal working conditions. And we're actually doing a regression analysis as we turn up those vibration motors. They're going to be running some analysis on the bridge to see if there are any structural issues. And we can go from normal to alert to critical or danger, depending on how much vibration is in these pathways. And with that, that's the end of our demonstration. You can also go to our YouTube channel and search for BrainChip Inc. And we have plenty of these demonstrations available there. And with that, I'll hand it back to you, David. Thank you.
Awesome. From here, I'll kind of move into a live demonstration of kind of what we've done to integrate MetaTF and support the Akida hardware today in Edge Impulse. Let me share my screen really quickly, and we'll just hop straight into that live demo.
All right, I'll stop sharing.
Perfect. Can everyone see this okay? All right.
Yeah,
so
you're good.
Awesome. So what I've got here is an early look at kind of what we're doing around integrating MetaTF and Akida as deployment options in Edge Impulse. And then we'll also talk about some of the future work we're looking into for closer integrations and just making this as user-friendly as possible. So what I've got today to start out is a really simple project that we're going to go through, working with a data set that you can build yourself in minutes to hours, kind of at home in a desktop environment, and then taking that and actually deploying it all the way out to the Akida PCIe enablement kit in order to see the live inferencing results from our spiking neural network that we'll deploy. So the use case in this specific project that we're going through is detecting fires. So if we're looking at the data set of this project, which is kind of all already imported and pulled into Edge Impulse, is you can see kind of it's going to be a lot of images of forests. We're going to have as well different images. I can pull up. We'll have different images from canned out online captured data from what a wildfire looks like. And then I've also added a few local samples of kind of a more desktop reproducible setup with an artificial fire source, which we'll see in a second. In order to kind of add samples like this, both to our training data set, what we're going to use to actually build our learning algorithm and build our model, as well as our test data, which is how we're going to validate the model's performance, how we're going to see, as you can see here, that, hey, my artificial candle with a kind of tree line out my window, is being inferred properly by our trained network before we go out and deploy it to hardware. Edge Impulse supports live data ingestion from a variety of devices. So out of the box, our Linux tooling can support cameras as well as microphones. And so here I'll enable on my device that's connected up to the Akida PCIe, I'll enable my my webcam ingestion. And so now we'll see the Linux device show up. We'll see the ability to select between the different sensor options. Here, of course, we're using the camera, and then we can define the type of label, the type of sample we want. Here, I want to make sure I'm not adding to my training data set. I want to work off of my existing kind of not exactly this setup. We want to make sure our model generalizes and kind of performs well in a slightly different kind of environment or setup. But we'll add some samples to our test data set so we can kind of benchmark how our model's doing during the training process. So I'll just kind of add a few samples here. And as you can see, they're just streaming right off of the device into our platform, and we can kind of get the early look at what that data will look like there. So once we've done this, and I'll highlight here that we don't just support live sensor ingestion. You can also pull in data sets from your local system, as well as explore pulling in large data sets from other cloud providers. That's all supported in the platform. And within this, we'll also be able to do some early data analysis that we'll see in a second, even before we get to training. But to get there, let's start and look at kind of what algorithm I put together for this demo project. So to start, depending on the type of data you pull into Edge Impulse, we're going to be looking at resizing the image down to kind of whatever makes sense for your end target camera sensor in this case, as well as optionally running some signal pre-processing on the data. Here, we're just going to use the raw image, but there's a variety of options available in the platform out of the box, including spectral analysis, statistical features, and frequency over time spectrogram type outputs, which is especially useful for audio, wake word detection sorts of use cases. But here, we're just going to take the raw image data and learn directly on that with our spiking neural network. And so when we're working with these pre-processing blocks, users also have the full freedom to implement their own. We support a very simple kind of plug-in method to add your own custom DSP. And some interesting examples is we've had people do edge detection, as well as distance field mapping and other types of kind of signal processing and image processing algorithms ahead of feeding that data to a neural network. And so you can use that as kind of an amplifier to get some manual feature extraction. If you're working in a sensor domain where you understand the properties, what you're looking for very well, you can go in and pull that data in, run those pre-processing steps, and kind of have that built into the platform first party. Additionally, when you get to the learning step, we have the same freedom. So we'll be able to both pull from existing Keras architectures, and we'll also be able to define our own, which is what we're doing here to really kind of get this first look at building a Akida compatible spiking neural network in the platform. And so with this kind of set, we'll really quickly go through kind of the image features, taking a look at those. So in this kind of view here, depending on your pre-processing, you'll be given a number of options here. There's not much to do. But what's really interesting is when we run this entire optional pre-processing step over our data, we'll be able to get a kind of feature map showing the relative clustering of samples in our data set and how they interact and kind of locally and globally kind of split out from each other before we even do any training. And so this is a really good way to kind of get an indication of, is my data suitable for this sort of algorithm? How difficult is it going to be for a network to learn? And while it's just kind of visual intuition, this sort of interactive ability to go through and check that, hey, you know, this completely red tree, you know, in the fall kind of overlaps a little bit with some of our fire data is an interesting kind of point that you might need to kind of drive further data collection or data cleaning efforts in order to kind of get the optimal performance in these kind of edge cases and complicated situations and image types. So from here, we'll go into the training block, which is where we're kind of looking again at our first look at kind of how we can build models for Akida. And I'll talk about kind of how this works today and what we want to kind of have in the future with our integration here. So as Todd mentioned and Nikunj mentioned, we are working directly from their MetaTF library. And what MetaTF allows you to do, which is really powerful, is take a Keras model and convert from that kind of CNN representation using their tools, convert to a spiking neural network. And so in our training view, what we're doing here is we're just training a relatively standard CNN defined in our expert mode, making sure it's a network that kind of fits well within how the Akida hardware is kind of and tooling is kind of set up to pull it in to a spiking neural network. And from here, we're able to run all of our standard training, data exploration, and validation tools. And then later at the deployment step, we'll be able to use features from MetaTF such as quantization-aware training, their 4-bit quantization, and then their final kind of model deployment capabilities in order to bring this to Akida. And so, you know, this is kind of that first pass of, hey, I want to build a model. And what we'll be working towards and what I'll have some kind of where to look for this sort of next step in the future is, hey, you know, how do we make this a little bit more built into the platform? How do we support out of the box these sorts of architectures? And how can we just make this as user-friendly as possible? And so what I'm showing here is kind of the existing trained model. It's a really small convolutional network. And if you look at kind of the accuracy and feature map metrics shown after training in the platform, you can kind of get an idea of how this model might perform just based on its training data. But this isn't really super accurate with regards to how it might actually perform in the field. So to do that, we really want to focus on testing on new data that the network's never seen before during training, and then also baking in the different quantization-aware training and deployment steps that we're going to do to get this model running on Akida. So to start with testing the network out on some new data, we're going to go to the model testing tab in Edge Impulse. And here we can see the existing results from the last run, where we've kind of gone through and seen that, okay, there's a small drop in accuracy from our very good validation results, but we're still classifying the majority of samples correctly, and we're actually classifying these more newly collected samples accurately as well. And so we can verify this real quick by rerunning. This should only take a moment to run, and we'll see how this kind of modifies, if at all, the test results. And so this is a really powerful tool. You can, as you're working through a project, either in a test bed or in the field, if you maintain the telemetry to pull in samples every so often, you can build up a real world test set that you can use to benchmark your models and algorithm designs as you iterate on them across different domains where you're going to be deploying your kind of model or product out to in the field. And awesome. So we were able to successfully classify both of those two new test samples that we added, which is a great sign that this will perform well when we deploy it out to the field. But there's one important step which is left, which is, as I mentioned, the kind of deployment stage. And so here we've added a couple of options within Edge Impulse that are designed to support different workflows between MetaTF, Akida hardware, and our tool. So the first option is we can deploy out as a kind of MetaTF library that you can take, go to the BrainChip kind of documentation sources, and you'll be able to, for image networks and kind of these sort of convolutional networks, you'll be able to plug those directly into either custom Python implementations or into Akida examples that are already shown on their page, and you'll be able to run inferencing on them. And so that's a really powerful tool for both kind of interoperation if you want to work on custom designs, or kind of have a little bit more exact kind of support for different, custom operations or different application logics that you want to really tightly integrate together with your inferencing. But if you just want to really quickly, in just a few seconds, prototype out a model and see it running, either in simulation, as Todd and Kuch mentioned, or on actual hardware, which I'll be showing here, we have the support built into an early access version of our Linux CLI that lets us automatically download a model, talk to the Akida developer enablement kit, and then hand it images that it's streaming from a live camera and receive back the inferencing results. And so that's what I'll show here. I'll just need to start the runner really quick. And then we'll go over to a local debug UI where we are viewing kind of how that model is performing in the real world. So let me just reload this page to get the latest and greatest. And there we go, it's fire. So what's happening here is our CLI is running on a small Linux board. That Linux board has the PCIe kit, Akida developer enablement kit, and we're getting those results back from Akida. And we're seeing this on the live webcam feed. So I can kind of live go through, move my fire out of the way. I've stopped the wildfire in progress. And then we can kind of get that instantaneous, rapid prototyping of, hey, did this actually work with real data on our exact hardware with the exact camera sensor that hypothetically we would be, wanting to use in production here. And so that's a really powerful kind of rapid validation and iteration tool that you can build on with the other features in the platform, building up test data sets, and testing different pre-processing and network implementations very quickly to explore the different space of kind of algorithm options and figure out what'll work best to kind of solve the actual problem that you're looking to solve when you're using Edge Impulse and when you're deploying out to Akida hardware. So that's about all I have for the kind of live demo portion of this. Let me really quickly stop sharing and I'll pass back for the last couple of slides here. And then we can talk about some of the exciting stuff that we have coming soon.
Okay, I'll share my screen again, David.
Thanks, appreciate it.
All right.
And could you move 2 slides forward?
Yep.
Oh, one more, sorry. Perfect. So on September 28th, in about a month, we've got our yearly event, Edge Impulse Imagine. It is going to be a both in-person, hybrid in-person online event where we're going to be highlighting innovation and new kind of developments and technology across the Edge ML and AI kind of ecosystems. Both BrainChip and myself will be there. We'll be presenting a lot of cool things. And one thing we're really excited to be able to demonstrate is both some upcoming features around tighter integrations between the BrainChip Akida platform and Edge Impulse, as well as some of the exciting demos that BrainChip is preparing around vibration analysis and smart infrastructure. So if you want to sign up, we'll have a link on the final slide of this presentation, as well as some other resources. And you can go ahead and hop to that next slide. And you can sign up to view remotely right from that link. And then there's also a few resources there to learn more about the different BrainChip use cases, examples. We have their YouTube channel here, as Todd mentioned. And then if you want to get started with Edge Impulse, if you haven't used it before and want to try it out, we have a really great quick tutorial sort of introductory model training tool you can go through via that Evaluate link. It'll just take about 5 minutes and it'll kind of show you the platform's capabilities in a really great way. And then finally, if you're interested in kind of getting a look yourself at some of these early access tools, feel free to contact hello@edgeimpulse.com and we can get you kind of sorted with maybe an early look at some of these exciting new features that we've got coming out. And you can start prototyping and building Akida models for your own products. All right, so with that, I think, Luis, I'll hand it off to you. Let's go through and cover any questions that came out while we were kind of going through the presentation and demos. Yeah, thank you so much for your time.
Great, thanks, David. Okay, so first question, can you provide examples of on-chip learning?
Sure, I'll take this one. On the on-chip learning, we use it for device personalization. It's really meant to do several things. One, when you've trained your whole data set, that last layer that you have, let's say it's in the in-cabin demo, we use it there to on-chip learn, your family, so that now I recognize me as I come into the car, I recognize Aaron or Nikunj with one shot. And with that, now I've recognized them, you can send, you can use that to personalize the car, applications for that particular person. So for instance, you may give me full access to all the car's functions, but my 16-year-old kid, I don't want them driving after 10 o'clock at night. So I can limit those functions as well. Or I want to give my children access to the infotainment system so they could watch TV in the back, but they don't have access to anything else. That's just one example.
Thank you. Okay. Were the 3 demo applications trained using the STDP algorithm, or were they converted from an from ANN.
Yeah, I'll take that one. Thanks, Liz, for the question. So, and I think the question came from Evolved. So hopefully I pronounced your name correctly. So essentially, thanks for this question. So the demos that we showed are trained regularly in TensorFlow environment, as I mentioned earlier, and they are trained on a public data set, right? So you can find these models available on our MetaTF platform, and hopefully see you soon on the Edge Impulse platform as well, where you can take these models yourself and create your own demos, or maybe transfer them yourself. And then in one of the demos, we showed an on-chip learning use case where I think a person stepped into the car, and even Todd stepped into the car, and they were able to recognize, hey, it's Todd, or it's the other person walking in. And so for that type of use cases, we build this on-chip learning algorithm on top of this model, and the algorithm is inspired by SCDB. So you'll be enabling a lot of neuromorphic concepts in building these models. Whereas if you are completely unaware of these concepts, you can go ahead and build your regular flow in TensorFlow and start moving from them.
Thank you. Okay. Will there be a dev kit to test out the chip with Edge Impulse?
I'll take this one again. So as I said before, we do have development kits and development boards. If you go to BrainChip.com/developer, and that links us to the MetaTF page. It says all the requirements. I think there was another question about Linux versions and stuff. So you can go to our MetaChip environment. It says all the requirements that you need, both hardware and software. You can acquire the BrainChip development boards, development cards at shop.brainchipinc.com. You can actually look at our enablement package, which is a little bit more support at brainchip.com/package or products as well. So everything is available today. And as David said, we are continuing to add more and more features into the Edge Impulse environment as time goes on.
Thank you. Is the Akida chip intended to run the main application itself, or is it more intended like a neuromorphic coprocessor?
I'll take this one too. It's meant to be a neuromorphic processor. So it's not meant to run the applications. You're going to run the AI inferencing piece of it. So you will need a host processor to run with it. On our development kits, as I stated before, the one on the left, which was a PC shuttle, has a Intel x86. The one on the right was an ARM-based Raspberry Pi. We have several different Raspberry Pi type boards that we work with. We're agnostic to the CPU, agnostic to the CPU. So we also have one using a RISC-V Sci-5 processor as well.
Okay. How are SNN trained, for example, for object tracking combined with an event-based camera?
Yeah, I think I'll take this one. So it's a really nice question. So essentially for the demo that we showed, we built off and we started off using a CNN algorithm, and it's tricky. I mean, it's really important to see what type of application you're building. With event-based cameras, you have events coming in a time-based series environment, and depending on the application, there are a lot of different techniques of pre-processing that could be applied, or different model approaches that could be taken. For this particular example, I think we took an encoding type of approach where we encode a lot of these information of time into some sort of a frame-based value, and it could be taken forward into a CNN-based architecture, right? And so that's how you could convert your existing CNN models, get your accuracy, and convert that to an SNN-based environment, and start running these event-based cameras on our neuromorphic hardware. And the nice part about this is when you start building these models with event-based cameras, you essentially skip the operations that you do of the frames, and you just take in those event values directly for the model processing, which is very tightly integrated onto a hardware. And if you're an IP customer, if you're kind of building your own ASIC out of it, you can really build a nice integration within the system itself, where you're really independent of the host in taking these raw values in and having that processed on Akida.
Okay. When you say that the Akida PCIe card is compatible with any Linux system, is that Debian Ubuntu, or might it include Red Hat and its variants?
So right now it's just a plug-in card if you take the plug-in card available, what you have available. So it can plug into the Linux-based system, and we provide the drivers for that Linux-based system. Now, if you're using our development systems, development cards, those are our development kits. Those already have operating systems in them. So it really depends what you want to do. Very flexible in how we approach it with our developers, end users, and hobbyists.
I think it's the same with the next question as well, Luis.
Yeah. Does the Akida chip support RTOSes like Zephyr and EmbeddOS? Yeah.
Yeah, for our reference chip that we have available in our development kits, we are on Embed. You can actually search for BrainChip out there.
Okay, so I think this is the final question. Oh no, two, sorry. Is it possible to deploy models for Akida processor with Edge Impulse if using data coming from event-based sensors?
Yeah, so I can take this one. So absolutely. So we actually have some prior projects before we've kind of added some of these early features around Akida integration that pull data in from event-based cameras into Edge Impulse, and then optionally can run different pre-processing techniques in order to kind of extract what you want from those sort of event-based, that raw event-based data. Now, exactly how that interplays with the example shown in the earlier slides, that structure would be entirely possible to replicate within Edge Impulse once we kind of have this fully featured Akida integration, just in the fact that we can pull in event-based camera data and we can either do pre-processing or just feed that raw data straight to an Akida-based learning algorithm. So absolutely.
Will we see neuromorphic chips everywhere for edge AI devices in the future?
So I'd like to see it. I mean, one of the things, if you guys have been paying attention to the industry, we believe neuromorphic is going to be very popular at the edge for how we do computation. You're going to get some of the advantages with traditional CNNs and how we extract features out of the data sets, but you get the optimized system solution to have overall low latency, low power, and very tight constraints that these edge-based devices have.
And I think finally, is the Edge Impulse platform hosted in the cloud or on the local device?
Yeah, so of course, everything we're deploying out is completely offline capable and local, but the platform itself for kind of ingesting data from different sources and offloading the training and signal processing jobs, that's all cloud hosted and is accessed through our website.
Great, thank you very much. Okay, I think that's the end of the questions. So thank you everybody for today. Thank you for joining. And we will share this live soon, so on demand soon. So if you keep an eye on your socials, then you'll see the link to it. Thank you very much. Bye-bye.
Thank you.
Thank you so much. Bye-bye.
Bye.